We're looking here at a picture of one of the most famous physicists who ever lived. His name is Richard Feynman, and he wrote a book in which he wrote this statement. He said, if in some cataclysm all of scientific knowledge were to be destroyed, and only one sentence passed on to the next generations of creatures, what statement would contain the most information in the fewest words? In other words, Feynman is saying, what is the most important scientific discovery that we've ever had? And this is what the statement turns out to be. All things are made of atoms. Richard Feynman is saying the most important discovery science has ever made is that all things are made of atoms. Physicists believe that. So do chemists. In fact, our science of chemistry is built on the idea that everything is made up of atoms. Since this is so important, I don't want you to just take it on faith. I want to give you good reasons to believe that everything is made of atoms by taking a look at the history of how we came to this belief. We'll start this history out a long time ago with the Greeks. The Greeks were the first people who left us a record of what they thought about matter. These people weren't really scientists, they were philosophers, which literally means wisdom lovers. There were two of them, and they had two different ideas about matter. This one is a guy you've probably heard of before, fairly famous, Aristotle. He was a very influential thinker. Democritus is not as famous, but he turned out to have a theory that was closer to being what we now believe today. Here's Aristotle's basic idea. We now think that matter is all the things that have a mass and take up space, and that energy is something that causes changes to matter. But he didn't make distinctions between the two of those, nor did anybody for many, many years. His idea was that everything was made up of four elements, only four. And here's what they were. Wind was one of them. Earth was another one. Water was another element, and the final element was fire. And everything was made up of a combination of these four elements, and it could change. For example, Aristotle might think that an olive tree that was growing, still alive, on a still day, would be made up of earth and water, because it's solid like earth, so mostly earth, but it is wet inside, and so it's made up also of water, kind of like what we still believe today. But here's where it gets different. On a windy day, he doesn't think that wind is causing the tree to have its leaves rustle. He thinks that the tree is actually gaining some of the element wind, and that's what causes the leaves to rustle. During a thunderstorm, the proportions just change. More wind, more water. These bar graphs that I'm showing are just a sort of a way of getting at his thought process. He certainly did not make bar graphs for us. In lightning, you saw a little bit of fire flash up and then disappear. Change in the composition. Tree is cut down and it dries out. No wind, less earth, no water. Somebody burns the tree. Fire enters, earth disappears, fire disappears, nothing left. The matter was destroyed. We don't believe that anymore, but that gave us a way to start thinking about matter. And actually, through the Middle Ages, that theory that everything is made up of earth, wind, fire, and water was really never disputed. People built all of their sort of scientific knowledge based on that. Democritus had a different idea. He didn't think there were four elements. He thought everything was made up of just one kind of stuff. But that stuff was divided into tiny particles, and he called these atomos. In Greek, you'd spell this like this, atomos. But our word atoms comes from that, and that was the basic idea. These atoms, he thought, were invisibly small. They were going to be so small that you'd never be able to see them. They were indivisible. In other words, you can't break them apart. You could smash things into small bits and smaller bits and smaller bits, but eventually you'd get to a bit that you just couldn't smash, and that was an atom. And then he also thought that they were differently shaped, and this was sort of a key to explaining why this would make sense, because it explained why different kinds of matter behaved in different ways. Here's an example. Liquid atoms, he said, were like poppy seeds in your hand. They would roll around because they were round. You couldn't see them, but if you could, he figured they'd be round. And that explains why liquids flow, because round things can roll over each other like poppy seeds in your hand. Solid atoms? Well, he thought that solids stuck together and pulled, when you pull on them, they pull back because they have little hooks on them. These little hooks explain the behavior of solids. Gases, he didn't believe things like hydrogen and oxygen, the inert gases existed. He didn't understand that. But he did know that there was some matter that made your nose hurt. things that smelled bad, and those were gases. And so he thought that these atoms must be shaped like this, had these pointy tips on them that were stabbing you in the nose, and that's why they hurt. Well, that was a fairly decent explanation for matter. This is all laid out in a big, long poem by a disciple of Democritus named Lucretius. Kind of interesting poem, but it's also a sort of a science textbook in a way. Well, Democritus' theory lost out. Aristotle's was more commonly believed through most of the Middle Ages and early part of the Renaissance period. But it turned out that Democritus was maybe closer to right. The next big change came along with this person here, Antoine Lavoisier. This is a French philosopher, scientist guy who is often called the father of chemistry because he did three things that really changed how people thought about matter fundamentally. One of them was he defined elements functionally. He said, first of all, there's more than 4 elements. There's a bunch of them. He didn't know how many. He thought maybe 8 or 16 or something like that. He had no idea how many that there were going to be. We've now discovered more than 100 of them. But his idea of an element is this. If you took substance A and you changed it into substance B, substance A could not possibly be an element because elements can't change into other elements. That was part of the functional definition. He also said that any kind of chemical change, what you're really doing is you're recombining elements that were already there. You can't create and destroy elements. The elements are there before and after the change. It's just some kind of a recombination or rearrangement, or somehow the same elements are there before and afterwards. It's not transmutation. So when a chemical change takes place, you don't destroy one thing and create another. You just rearrange sort of what was already there. He didn't know exactly how that worked, but he knew that the elements weren't being changed. They weren't being transmuted. And then the third thing they did that was really important was he developed a systematic naming system. And this naming system was based on what elements were there and how much relative proportions. We still use his naming system, even though now we understand way more than he ever could have about why his naming system made sense. Not much else happened until this guy came along. The next big advancement came from this man here, John Dalton. John Dalton was a high school teacher. He started teaching high school when he was still a teenager. He was never allowed to go to college because at the time he was not a member of the Church of England. You had to be to go to university. He was a Quaker. He had a different belief system, and so he kind of was self-taught. He was really interested in meteorology, and as he was doing some reading to try and become better at understanding meteorology, he uncovered 2 phenomena that didn't have explanations. One of them we can see here. This is a chart that shows different masses of water, and these are the sizes of the samples, 18.015 grams of water, 0.4993, and 50.3. If you take water, which is made of hydrogen and oxygen, 2 different elements, and you split up the hydrogen from the oxygen, just break the compound apart, collect all the hydrogen in one place and weigh it, collect all the oxygen in one place and weigh it, this chart shows how it breaks down. In other words, that 18.015 grams of water is 15.999 grams oxygen and the rest hydrogen. If I take from sample 1 2.016 grams and I divide it by 15.999 grams, I'll get some number. Let's find out what the number is. 2.016 divided by 15.999. Here's what it comes out to be. 0.126 is the ratio. Let's do the same thing for sample 2. With sample 2, we've got for hydrogen 0.05587 grams divided by 0.4434 grams of oxygen. Let's check this ratio. 0.05587 divided by 0.4434. Well, it comes out to be 0.126. Well, you probably already know what's going to happen when I take 5.63 grams of hydrogen from sample number 3 and divide it by 44.7. Sure enough, it does come out to 0.126. You can check it if you don't believe me. But this was the thing that was interesting to them. No matter how big of a sample, like as big as 50.3, or how small as less than a half a gram, or anywhere in between, or any size sample, when you did this decomposition separated the elements and made this ratio, it was always the same ratio. There might be a little bit of experimental error, but it basically came out to the same thing every time. Because this always happened, because it was never found to fail, we have something called the law, and it was called the law of definite proportions. The law of definite proportions says this: every time you decompose a sample of the same compound, the ratio of the masses of the elements is the same, no matter how big, no matter how small. So if you have a compound that's made of element C and element D, for example, if you were to take the mass of element C and divide by the mass of element D, no matter how big or small of a sample, you will get the same number, the same ratio every single time. This is a different compound. It's hydrogen peroxide, also made of hydrogen and oxygen. This chart shows the same thing. 3 different samples, one big, one bigger, one really small, divided up into the masses of hydrogen and oxygen that are in them. Let's look at these ratios. If I take 2.016 and I divide it by 31.998, what do I get? Well, here's the number that I get. I get 0.063. If I do this for the next compound, or the next sample, 0.0198 divided by 0.3148, I'll get the same thing. I'm going to get 0.063. If I do it for sample number 3, that was 1, this is 2, do it for sample number 3, now I'm taking 1.7 and I'm dividing it by 26.9. It's a larger sample, but again, I get 0.063. This didn't just work for compounds of hydrogen and oxygen, and it didn't just work for water and hydrogen peroxide. It worked for every single thing. So it's a law, but nobody had an explanation for it. Here's another thing that started to happen. This is a little more subtle, it's more sophisticated, but scientists were also noticing this. If you had 2 different compounds made of the same elements, like in our 2 examples that we just had, water and hydrogen peroxide, they're both made of hydrogen and oxygen. If you get that hydrogen-oxygen ratio, like we saw for water, it was 0.126, and we saw for hydrogen peroxide, it was 0.063, and you divide one by the other. So let's say we take 0.063 and we divide it by 0.126. Here's what you get. You get 0.5 in this case, or 1/2. And if we had done this the other way around with the 0.126 on top, we would have gotten 2/1. A simple whole number ratio, like a 4th grader fraction. Well, this always happened also. Anytime you had 2 different compounds made of the same elements, every time you decompose samples of 2 different compounds made from the same elements, the ratio of the masses of one element per unit mass of the other is always a simple whole number ratio, a simple 4th grader fraction. Let's look at another example. Here's water again, and again there's that 0.126 hydrogen-oxygen ratio. Glycerin is another compound that has hydrogen and oxygen in it. The ratio is 0.168 of hydrogen to oxygen. If we take 0.126 and we divide it by 0.168, here's what we get. We get 0.75, or 3/4. Had we done it the other way around, we would have gotten 4/3. No matter what, simple whole number ratio. It happened every time. This was a law, again, that had no explanation until John Dalton came along. Well, Dalton thought there should be an explanation for this, and it must have to do with something really fundamental about what matter is, how it behaves. And so he came up with this atomic theory, sort of a rebirth of Democritus' idea, only this was based on scientific evidence, not just a philosophy. We're going to explore Dalton's atomic theory in 3 postulates, or 3 statements. The first one is this: all matter is made up of atoms. Everything is made up of atoms. So there's that atomos again, those little tiny particles, which are indivisible. In other words, there's nothing smaller than that. You can't break them up. And they cannot be changed. So he's borrowing Lavoisier's idea that you can't change elements from one to the other. But he's also borrowing Democritus' idea that everything is made up of atoms that are indivisible. Atoms of one element are identical. In other words, every hydrogen atom is going to be exactly like every other hydrogen atom, all the same. But they're different from atoms of all the other elements. So hydrogen will never be the same as a carbon or an oxygen or a nitrogen. Never. The third postulate, this is really the big one that explained a lot of stuff. The only difference between 2 compounds that have the same elements in them is the number and the arrangement of the atoms. So it's the same atoms, but they're just arranged differently, or there might be more or less of them. Why was this a big breakthrough? Well, it was because it explained both of these mysteries. How does it explain the law of definite proportions? Well, let's imagine that we have a compound. This is just a fictitious compound made up of red atoms and white atoms. So here are two of these little clusters, a sample size of 2. Well, Dalton says if you break these things down, if you decompose this, what you're really doing is you're just taking apart atoms it was made of. So here we see a progression. You take these atoms, remove the sticks, the bonds, the glue that holds them together, and you got separate atoms in this compound, in this sample. If you separate the red atoms from the white atoms, put them in different places, well, you have atoms that weigh a consistent amount here, and 4 atoms that weigh a consistent amount here. What if we were to actually physically take these little plastic models and weigh them? Well, I've done that here. Here's 3.33 grams for the 2 red atoms, and 1.94 for the 4 white atoms that we got from these 2 clusters. Let's find a ratio. 3.33 red mass to 1.94 white mass. 3.33 divided by 1.94 is 1.72. Let's keep that in mind. Let's look at another sample of the same compound. Here again you see the same cluster, 1 red to 2 white, but now we have, instead of 2 of them, we have 4 of them. Split them up the same way, regroup them, and you find 4 reds to 8 whites. Well, the ratio of particles, the ratio of atoms is still the same, and the atoms all weigh the same amount, so the ratio of masses should be the same. Let's see if it is. Here I have my balance. It's got my 4 reds and my 8 whites on it. Let's look at the ratio. 6.64 grams of red to 3.86 grams of white. Now remember, what we had before was 1.72. It's actually still on my calculator. Let's see if we get the same ratio. 6.64 divided by 3.86. It's 1.72. That's the law of definite proportions explained. It wouldn't matter if we had 2 million or 4 million or 4 trillion or 2 or 4. The ratio of particles is always going to be the same, and since the particles are all identical, the ratio of masses should be the same too. Now, there's probably not only one way to explain that, so this doesn't really prove anything, but it does match this law, this phenomenon that was never known to be violated, and so it gained some traction. People started to believe in it. Here's the next question. How does Dalton's theory explain the law of multiple proportions? Well, let's take a look. Imagine that we have 2 different compounds, again made of the red atoms and the white atoms. This is the one that we just looked at. It's a 2 whites to 1 red ratio, and this is a 2 reds to 2 whites compound. If we could split this up and separate, here's what we'd find for the left-hand compound. 8 reds, 8 whites. For the right-hand compound, 4 reds to 8 whites. Let's look at the mass ratios. For the left-hand compound, this top balance has 13.35 and the bottom balance has 3.86. So here's our ratio. 13.35 to 3.86 is 3.46. Let's keep that in mind. Now, on the right-hand side, I've got my right-hand compound. 4 reds to 8 whites. Look at the masses. 6.64, 3.86. Let's find out what that ratio is. 6.64 to 3.86, 1.72. Seen that ratio before. Okay, now the law of multiple proportions says this ratio and this ratio, if you make a ratio of those ratios, you should get some simple whole number ratio. So let's try it. 3.46 divided by 1.72. Look at that. 2 to 1. There's our simple whole number ratio. Because both of these phenomena were explained by Dalton's theory, people came to eventually accept it as the right way to understand how matter behaves. It took about a generation because Dalton wasn't really well respected in the scientific community because he'd never been to university. But eventually it caught on. Dalton was not completely right. We'll find out later that one of his postulates about them being indivisible turned out not to be true. But the basic idea that everything is made up of these little interchangeable, like blocks of matter, these atoms, that explained everything that they knew, really was a great explanation, and it formed the basis for a much greater understanding of how matter behaves.